Okay, well, this is going to be an interesting lecture because this is a makeup lecture with nobody in the room that we're having to do because we forgot to turn our sound on last time. So any questions that I ask are going to be exclusively for those of you who are out there watching in video land. Okay, today is our first day of a big journey into predicate calculus. So let's recall the distinction between propositional calculus and predicate calculus. Okay, now can you tell me what's a proposition?
True or false.
Yeah, a proposition is a declarative statement that is either true or false. So all of the Boolean expressions that we dealt with, the theorems that we proved, and the axioms that we assumed, they're all based on expressions where all types are Boolean. So, based on expressions where all types, based on expressions where all types are Boolean. Just to give you an example, suppose we have something like this. P and Q implies R, okay? So the thing that we know about an expression like this is that each one of these variables, like the R here, it's type Boolean. And then we know you know the definition of an expression, right? The first thing is an expression is what? Either constant or variable, and then if E is an expression, blah blah blah. Okay, so we know so all of these so this is, each one of these individually are Boolean. Each one of these variables has Boolean type. And then the expression, the whole expression is a Boolean expression, and this is a proposition. And the propositions that we dealt with were validities, which means that they are true in what? True in all states. What's the definition of state? It's a list of the variables and their values, right? So that's the propositional calculus. Now what is a predicate?
I realize when you act like somebody's here, you've already prefaced this with the fact that nobody's here. So I can get that.
Well, I'm asking the questions to those of you who are watching this on video. Okay, so what is a predicate? Anyone remember what the definition of a predicate is?
A function that returns a Boolean.
That's correct. It is a function that returns type Boolean.
It's almost like a third time. I think.
Right, it is. Now, so it's very, I mean, Boolean is involved in both of these, but what's a key difference here? A key difference here is that a predicate is a function, whereas a proposition is a declarative statement that's either true or false, right? So what is a function? Well, a function returns a value. A predicate is a function that returns a value of type Boolean. Okay, but even though it returns a type Boolean, its parameters do not have to be Boolean. Okay, so it returns type Boolean, but whose parameters might not be Boolean. Okay? So let me give you an example here. Here's a predicate. Odd dot n. Now, what do you suppose the type of n would be in odd dot n? It would probably be like integer, right? Big Z, int. So even though this is an int, but on the other hand, you know, odd dot n is either true or false. In other words, odd dot 6 is false, odd dot 7 is true, right? Because 6 is not odd and 7 is. Yeah? You with me? So here's an example of a function that returns type Boolean, but its argument is not type Boolean. Here's another one. Ooh, this one is, how about this? Equals. Suppose we say equal, you know, like x plus y comma 3. Okay? So the equals function is Boolean, right? So 3 is an integer. The expression x plus y is it's an expression that has type integer. And so if x plus y does equal 3, then equal this returns true, otherwise it returns false. So here's another example. And what by the way, what's the, remember, I think, on the last exam, I think you had to tell me what's the type of equal when considered as a function? It would be, if these are integers, right, it would be what? Z cross Z arrow B. Yeah? Okay, so that's the type of equals when considered to be a function. Okay. I guess we'll just stay on this side of the, we're actually even in a different room from what we're used to on this retake, take 2. Predicate calculus, take 2. Okay? So, now, what is then predicate calculus? Predicate calculus. It uses predicates and universal and existential quantification. Uses predicates and existential, big word, existential and universal quantification. Okay? So, let me give you an example of universal quantification. Consider this. For all I, range 0 less than or equal to I less than n, body b sub I equals 0. Okay? Let's consider this quantification. This now, what is the operator for all? Do you remember that? It's and, yeah. So this is and. So and now, what are the possible values of I here? 0, 1, 2, 3, all the way up to what? N minus 1, yeah. And here, what did we say? What is the type of this whole thing? The type of this whole thing is the type of the body. So if the type of the body is, well, what is the type of this body? It's Boolean. B sub I equals 0 is either true or false, right? Okay, so this is type Boolean. Because that's type Boolean, the type of the whole thing is Boolean, right? So if you were just to expand this out, what would this be? Well, the possible values of I are 0, 1, 2, etc. So, and for all is and, right? So it would be B sub what? B sub 0 equals 0, and B sub 1 equals 0, and B sub 2 equals 0, and etc.
Don't use green.
Okay. All right? So this is an example. So actually, now let me ask you this. Is this I here, is it bound or free?
Bound.
It's bound because it's bound to this I. This is the dummy variable I. How about this n? Is it bound or free?
Free.
It's free. So the n would, if you were to expand this out, the n would appear in the final result, right? So you can think of this, oh, what about the b? Is it bound or free?
Free.
It's free, right? Okay, so you can think of this whole thing as being a function of n and b. But what type does it return? It returns Boolean, right? So you can think of this whole thing as being a predicate. Okay, this is a function of n and b, and it returns type Boolean. Okay, so this is a function of n and b, returns type Boolean. So therefore that makes it a what? Predicate. So it is a predicate. Okay? Now think about this. Let's contrast that. How about we do this? Sigma I, 0 less than or equal to I, less than n, body b sub I. Let's think about this quantification. Now what's the operator for sigma? Plus, addition. And so what do we have here? The possible values of I are 0, 1, 2, 3, 4, just like before. But now what is the type of b sub I?
Whatever the type of the array is.
Yeah, whatever the type of the array is. Yeah. So b, let's suppose it's an array of reals. Okay. So suppose this is a, what was the symbol for real numbers?
Double R.
R?
Yeah. What if you do ends?
Okay, yeah, but let's just say it's an array of real numbers, right? Because, and if you were to expand this out, what would it be? The first few terms would be what? Well, I starts at 0, then 1, then 2. So it would be b sub 0 plus b sub 1 plus b sub 2, etc. And so you'd be adding these real numbers together, and so the expression would be a real number. Yeah? Okay? So, does it return type Boolean? No. So, does not return type Boolean. So this one is not a predicate. Because a predicate is a function that returns type Boolean, and this does not return type Boolean, right? Okay, so with that brief review and intro of review of some of these terms, now let's take a look at our first big step into universal quantification. And the first thing that we want to note up on our slide here is this notation. And I think we've mentioned this notation before. And notice the first line. Notation, star x, range. And now if you don't have anything between the vertical bar and the colon, that does not mean the empty range. It looks empty, but that's not the empty range. What does it mean? It means true, okay? So anytime we say star x, or anytime we see what that quantification is, we're going to say star x, range true, body p. So we'll just get used to saying that. If there's nothing in the range, it's range true. Now, do you remember what did we do an empty range? I think we had an empty range rule, didn't we, before? Let's go back and let's take a look at this.
X is also
I think there was an empty range. Here, let's look back here on 8.13. Check it out. What did we say is the empty range on 8.13? The empty range is when the range is what? False. Okay, so that's what we mean by empty. When we say empty, we mean the range is false. And we had this axiom, empty range rule, and what was that? We said that star x, range false, body p equals u, and u was the what? The identity of the operator. Now let me see, what kind of operator is it that we can have, that we can quantify over? It has to be, what was that called? Starts with an A. Remember? Abelian monoid. And what were the three properties of an abelian monoid? The first one is, it had to be what?
reflexive. No, symmetric.
Symmetric, yeah. Symmetric,
Associative.
P star Q had to be Q star P.
Yeah.
Associative, and it had to have a what?
Identity.
It had to have an identity, and that U is the identity. The reason that it has to have an identity is so that we can use the empty range rule there. Okay? That's a requirement to be able to quantify. Okay, so that was a little review of our terminology. If there's nothing there, it means range true. Okay? All right, now let's take a look. First of all, let's see if we can understand why 9.2 makes sense. Now, what's it saying? I mean, you've got, what is on the left-hand side of 9.2 axiom? It's for all x, range R, body P. Yeah? Now, what is always the type of R?
Boolean.
It's always type Boolean. The range is always a Boolean. It's a Boolean expression that, and what you do is you quantify over that a value in that, for all those values for which the range is true, yeah? So what's it saying on the left-hand side? It's saying that if you have a situation where for all x, satisfying range R, that's the same thing as saying, that's equivalent to saying all x for every possible value of x. Not just satisfying R, but for every possible value of x. Now, how would you know what every possible value of x is?
Depends on what type.
It depends on its type, because what is a type? Remember what the definition of a type is? A type is a what? It's a collection of values, right? So remember, like if the type were, suppose the type were natural number, then all the natural numbers would be 0, 1, 2, 3, 4, 5, 6, 7, 8, all of them, right? Okay? So let's just suppose that x is of type natural number, that x has type natural number. What this is saying is, on the left-hand side, it's saying for all of those x's that are natural numbers, for those that satisfy R, P is true. Now what's it saying on the right-hand side? It's saying for all x, not the ones that satisfy R. In other words, for all of them, 0, 1, 2, 3, 4, 5, all the way up to infinity. But what it says in the body now is R implies P. In other words, if R is true, then P is true. Does that make sense? That's kind of general. But, and of course we don't prove this because this is an axiom. But this is the fundamental definition of universal quantification. Are you with me? It's axiom trading. Okay? Now, what about 9.3 trading, ABC? Well, are these axioms or are they theorems? Well, it doesn't say axiom, must be a theorem, right? So therefore, what must we be able to do?
Prove.
We must be, but, whoa, I think it's pretty easy, don't you? What about 9.3a? Look, it says for all x, range R, body P, that's equals for all x, range true, body not R or P. But wait a minute, I think this is just a one-stepper, right? Because how would you do it? You'd start with the left-hand side for all x, range R, body P, right? Equals by 9.2 for all x, range true, R implies P. But isn't this our old friend? Who's our old friend? Do you have your equation sheet with you? 3.59. Yeah? And not only that, you know, it's a one-stepper to do 9.38 by, and what about B? And what about 9.3b?
3.5.
I forget, it was 6 something.
16, 61.
Is it 6? Yeah. Do we, here. Actually, Yeah, if you have your equation sheet out, it's 3 point, it's, you know, it's those ones with the the definitions of implication. One is 3.57 and the other one is 3.59 and the other one is 3.60. I forget, so the R and P equivals R, that's 3.60, and the R or P equivals P, that comes from 3.57. Yeah? So those are easy. It's just a one-step proof. What about the 9.4? Let's see if we can prove 9.4a. 9.4a is another trading theorem, but now it's a little bit more complicated, right? Because we have a Q and R in the range, and what we're trying to do, or what we're claiming here in this theorem, is that that equivals for all x. So now Q is staying in the range, but then the R goes out, and then it's R implies P. How can we prove that? You have an idea how we can prove this? Let's try it. Let's proof of 9.4a. Now, let's see. This is an equivals, right? So our strategy is usually to start with one side, get it to another. I think what we'll do is we'll start with the left side, okay? So let's start with the left side. For all x range Q and R, body P equals by what? Well, I mean, how much, you know, we don't have a lot to work with, right? I think probably what we should do is we should go up to our axiom, because in our axiom the range is R. Here our range is Q and R, right? So let's go up to our axiom. And our axiom is which? 9.2? And so what is this? For all x range what?
True.
True. Now body, so now the body is going to go be Q and, oops, I started to write out and. Q and R implies P, right? What now? Now what are we trying to get this to? We're trying to get the Q, we want to get the Q back into the range just all by itself. But here we have a Q and R, and what do we want to have in the, what do we want to have left? We want to have R implies P, we want to have R implies P left. How are we going to do this? Does this look familiar? Do we have some patterns? Where's our, how can we do that? Oh, did somebody say shunting?
Shunting.
Out there in video land? Oh, I think I heard somebody say shunting. Okay, so what is shunting? Shunting is what? You have your equation sheet, 3.65, right? So it's P, what is it? If you have P and Q equals R, that's P implies, sorry, if you have P and Q implies R, that's equivalent to P implies Q implies R. So this, what number is that? 365. So this equals by 3.65 for all x range true. So now this is going to be Q implies R implies P, right? By shunting. But now, what? We go back to 9.2 again, only this time, this is our P, yeah? This whole thing is our P. So this equals by 9.2 for all x range Q, body R implies P. Boom, we're done. Are we good? Are you with me?
Good.
All right. Good deal. So that's 9.2. Proof of 9.4a. And you know, you could do similar kind of manipulate. Oh, actually, B, C, and D come from A. They're just one-steppers again, right? They're one-stepper, you know, we don't even need to bother between B, C. That's just, you could almost do that in your head, B, C, and D. Okay, let me make a comment here about 9.4.1. Anytime you have two decimals here, then this one's not in the book, but it's in our equation sheet, and these are ones that I have come up with that I found useful for later on. So here's, this is called universal double trading. So double trading, what you do is you swap, it allows you to swap the range in the body. So for all, you know, it's like, you know, trading, see, trading gets the range, moves the range to the body, okay? And so what you do is you trade to get this range to the body, then you trade again to get the P back over here. And if you do that, you can show that, you can prove that for all x range R body P, you can switch the R and the P, but they become negatives. So for all x range R body P, that's equivalent to for all x range not P body not R. I think that's easy to prove. I was wondering if I'm asking you, actually, let's prove it. So easy to prove, let's prove it.
You want to do it the lesson we did it yesterday?
Yeah, now what's interesting was, in class, yeah, I did it a certain way in my notes, and in class we came up, a student came up with a slick way to do it that wasn't like the way I did it. So we can do either way. Let's do it the way the student said to do it. I like it better too, actually. So proof of 9.4.1. So we'll start with, for all x range R body P equals, now what I had done is I had done 9.3a. But I think what the student suggested, instead of doing 9.3a, I think the student suggested doing 9.2.
Yeah.
All right? So this equals, by 9.2, for all x range, by 9.2, it would be for all x range what?
True.
Range true, body R implies P, right? But R implies P, how do we flip these? Contrapositive, right? Oh, this is much nicer. I'm going to have to change my notes for next year. Okay, so this equals by contrapositive. I forgot the contrapositive. I don't want to look up the number for contrapositive, so we'll just put the name. And so that's for all x, range true. And the contrapositive of R implies P is what?
Not P implies R, not R.
Not P implies not R. Are you with me? Slick, huh?
Can we do that step? Is that valid? Can we just do the operation on the body?
We're substituting equals for equals. Yeah, are you with me? So the reason we can go from here to here is because we know this equivales this. So you can always do Leibniz. You can always substitute equals for equals anywhere, right? So this equivales this. So we're substituting equals for equals. Okay? And now, but now we go back and use 9.2 again. So this equals 9.2, but of course it's 9.2 with, what is it? 9.2 with RP replaced by what?
Not P, not R.
RP replaced by not R, not
No,
P.
not P, not R.
Sorry, not P. not P, not R. Okay, and so then that's for all X, range not P, body not R. Boom, we're done. Yeah, that's pretty slick. See, isn't this nice? Isn't that great how you've got this great facility now, and you know all of those propositional calculus theorems that we know really well now, and we use them over and over again, and now we continue to use them as parts of our proofs whenever we deal with these predicate calculus expressions. Okay, this whole system is just very, very nice. It's quite nice. Now, let me indicate then a few homework exercises that you'll be doing. 9.5 is an axiom. Okay, so we're not going to prove 9.5 because it's an axiom. What it says is that it says that OR distributes over for all, right? There's a proviso. Because if X cannot occur in P, because if X did occur in P, take a look at the left-hand side of 9.5. If X did occur in P, would it be bound or free? If X occurred in P on the left-hand side of 9.5, if X occurred in P, would it be bound or free?
Free.
It would be free. On the other hand, if X occurred in P on the right-hand side, would it be bound or free?
Bound.
It would be bound. So those would be different X's. Okay? So you can't move P inside of the You can't move P to the inside of the quantification, into the body of the quantification, if there is an X in P. So if you wanted to do that, what would you have to do? You'd have to do dummy renaming of the X, change it to Y or something like that. Yeah? Or change it to something that's not in P. Yeah? And then you could move it in. All right? And that's an axiom, so we don't prove it. But it makes sense because what is the operation for all? What's the operator? For all. It's and. So, I mean, you know from our propositional calculus that OR distributes over and. So it's kind of like that. That's why we have that axiom there. Okay? 9.6 is an exercise for you for the homework for next time. Provided not occurs, da-da-da. Okay, so you'll prove 9.6 for me. 9.8. Ooh, that's an interesting one. For all X over range R body true, equivalence true. That's also a homework assignment. Now this is kind of tricky because, you know, you can't just say, oh, well, it's obvious. I mean, you have to use, you know, you have to use Leibniz. You have to, you know, we have to, somehow, how are you going to get that to be true? Do we have any, where does true appear anywhere else? I don't know. You're going to, that's, you know, you have to, how are you going to prove 9.8? You'll prove 9.8 for me. How about 9.9? 9.9 is another one that you will prove for me, right? That's a homework assignment. It says that for all X range R body P, that's equivalent to for all X range R body Q, only under the condition that if for all X range R P equals Q, then that's the case. Okay? Which makes sense if you think about it. 9.11 is another homework exercise. Okay? And 9.13 is another exercise. As a matter of fact, 9.13, oh, I think I'm getting mixed up now of what I said in this lecture and what I'm, because this is a retake. I think I handed out the equation sheet, the worksheet for 9.13 in the other lecture. Okay? So now, what I would like to do now is prove 9.7. Okay? Let's think about what 9.7 is. Actually, I don't think we'll have time to prove it, but we'll at least get it set up, and we'll commence with the proof at the start of class next time. which was last time, because this is the second take, well, whatever. Okay, so theorem 9.7. All right, now let's just see if we can think about this for a moment. What does 9.7 say? Well, 9.7 is a great big implies, right? Let's take a look at the consequent. You know, and it implies the antecedent's on the left, the consequence is on the right, yeah? So in 9.7, the consequent is the following. For all x, range R, body P and Q, equivalves P and for all x, range R, body Q. Now, let's just take a look at what this says. What this says is that if you have a P and Q in the body, and the operation here is and, yeah? So if you have a P and Q in the body, you can pull out the P. You know, it's kind of like you can factor it out, yeah? Okay? Because what this is pulling P out, all right? So the P, it used to be P and Q here, but what this says is that these two are equivalent. But now, the thing about this is, you can't always do this. What does theorem 9.7 say? It says if, whatever that is, it says if not for all x range true, not R. So theorem 9.7, the theorem says, here, the theorem says you can do this if what? What does it say? If what? Not
for all x range true, body not R.
Not for all x range true, body R. No, wait, is it body R or body not R?
Not R.
Not R. Body.
And that not occurs P and X.
Yeah, plus the proviso. Okay, so we always have that proviso. But that proviso is to make sure that we don't have any free variables here that would become bound if we put it in. Yeah. Okay, but what is this? Okay, the theorem says you can do this if this. In other words, but what is this making a statement about? This is making a statement about the what? The range. This is making a statement about the range, yeah? And what does not R mean? It means the range is false. Okay? And what does this mean? What does for all? This means for all x, we have not R. In other words, everywhere, for every possible value of x, we have not R. But it's not that. In other words, the theorem says you can do this if this. I.e., in other words, if the range is not everywhere false. That's what it's saying. It's saying that you can do this as long as the range is not everywhere false. If the range is everywhere false, you can't do this. But if the range is not everywhere false, you can do that. Yeah? That's what this is saying. It's making a it's kind of a more complicated proviso than an occurs proviso. You know what I mean? All right. So much for our little take two. I hope the audio turns out to be good when we upload this, because I'm in a little bit of a time warp. I'm, a little confused about what we're going to do, which is what we did, but isn't time travel wonderful? Okay, see you next time, which I think will be Thursday, and hopefully no more audio glitches. All right, see you next time.